you are ready, I think we should start. Okay, so welcome everyone. It is my pleasure to welcome you to this seminar in the series of seminars that we have in the PhD program. Today with us we have Daniel Selva. All right, so let me introduce him very briefly. Daniel is an associate professor at the Aerospace Engineering Texas A&M University, okay, where he directs the Systems Engineering, Autonomy and Knowledge, or SEEK lab. His research interests focus on the application of artificial intelligence, knowledge representation and reasoning, planning and scheduling, multi-agent coordination, and machine learning to space system design and operations. Before doing his PhD at the MIT, Dr. Selva worked for 4 years in Kourou, okay, in the French Guiana, as an avionics specialist within the Ariane 5 launch team. Dr. Selva has a dual background in electrical engineering and aerospace engineering, with degrees from MIT, Universitat Politécnica de Catalunya in Barcelona, and Supego in Toulouse, in France. Between 2018 and 2022, he served for the European Space Agency in the Advisory Committee for Earth Observation. And Dr. Selva is an associate fellow of the American Institute of Aeronautics and Astronautics. He has received the 2023 Texas A&M Engineering Young Faculty Fellow Award and the 2025 Teaching Impact Award. Okay, so I hope I was correct on everything I said, Daniel.
Yes, that was all correct. Thank you.
Okay, so well, the floor is yours. Let me add that Daniel will be visiting us next in the next academic year in a sabbatical. All right, so I think we will have plenty of time to interact with him, and that is a very nice thing that we have. All right, so the floor is yours.
All right. Thank you very much, Mario and Eduardo, for the opportunity to talk to you all today about my work. I want to start by acknowledging my collaborators here. So this is a joint project with the University of California, Los Angeles, UCLA, Virginia Tech, NASA Ames, and the Jet Propulsion Laboratory. And it's all funded by the NASA Advanced Information System Technologies Program in the Earth Science Technology Office. So, of course, as always in academia, most of the work that you're going to see today is the product of my PhD students, particularly two of them for today's work, Alan Aguilar Jaramillo and Ben Gore. So with that, I want to delve into the topic of today's seminar, which is about autonomous Earth observing sensor webs, and particularly looking at this idea of coordination strategies in these sensor webs. So just a very quick introduction of the SEEK lab, my lab. You know, we're always hiring, right? So if anybody's interested, I guess you can feel free to shoot me an email. So our lab works at the intersection of AI, space systems, and systems engineering. Lately, we've been doing a lot of work in this area of task planning and scheduling for Earth observation constellations, like what I'm going to talk about today. But we're also working on other areas within that Venn diagram. We have also a pretty active focus right now on using AI agents to support fall diagnosis, fall detection, diagnosis, and recovery in crewed spacecraft. So, say Gateway or the ISS, and we also have a number of flight projects. Actually, we participated in the Tropics mission, which is flying right now, and now we have another mission called Gratis, where we're playing a role in terms of systems engineering and operations. All right, so with that, I want to start introducing this project called 3D Chess. So 3D Chess, then it's an acronym, and I didn't come up with it. I think it's a really cool acronym, but it was our collaborator at UCLA that came up with it. So the idea, so the definition, I guess, is dynamic, distributed, and decentralized, context-aware, heterogeneous sensor systems, which is a mouthful, but basically the idea is the core of this autonomous sensor webs concept. So it's having satellites, UAVs, and ground sensors all doing onboard data processing, detecting events of interest, communicating in real time, coordinating in real time to decide who's going to do what in terms of responding to these events of interest. All of this with the hopes of improving the response time to these events. We could be talking about things like floods, for example, that require prompt response, or just improving the sampling, spatial and temporal sampling of these events of interest. So in the 3D chess project, the goal was to get to TRL3, if you're familiar with technology readiness levels. So that means proof of concept for this autonomous sensor web network. And we're demonstrating this via simulation primarily for now, in the context of an inland water ecosystem monitoring. So you can see here in the plot the inland water ecosystem where there's multiple things going on, but we have rivers, lakes, reservoirs. There can be variations in the water levels in these water bodies. There could be things like algae blooms forming. There could be ice jams. There could be smaller rivers that kind of like dry out and then appear again. So essentially, these are the kinds of events of interest that we'll be talking about throughout today's presentation. So this is kind of the motivation. These inland water bodies, they can change state very, very fast. Floods, algal blooms, they can evolve in a matter of minutes to a few days. And climate change is not making that any easier. It's actually accelerating the pace at which these events occur and the intensity of these events as well. So we really need more spatiotemporal sampling of these events of interest with different types of sensors: visible, near infrared, thermal infrared, radar altimetry, etc. So in order to cut on the response time and improve the spatiotemporal sampling, it's really critical to invest in autonomy technologies. So we can continue with the concept of operations that we have today, which we rely heavily on human operators, essentially, waiting for the data to be processed by people on the ground, and then based on that, constructing a new plan for the constellation, and uplinking that plan at the next contact opportunity. That leads to response times on the order of hours, if not days. And that's not enough to respond to some of these events of interest. So we're after this idea of autonomy, and this is going to require being able to make decisions in a specific context. So that's the context awareness part. And in order to enable the response time, we're also going to have to rely on decentralized control and coordination. So we'll see what that looks like in the next slides. This is kind of like the comparison to the state of the art. We're really looking for networks where agents or satellites, UAV sensors can reason not only about their own state, or even not only about the state of the Earth system, but also about their own capabilities. So essentially, in order to autonomously coordinate, sensors in the network need to know what other sensors are out there, what are the capabilities of the other sensors, and who's in a better position to perform the different tasks. So the other idea is that we want these networks to be able to handle multiple dynamic objectives. So we're not talking just about a constellation to measure one thing, or even a few things that are always the same. We're talking about a constellation that has the ability to adapt to changing mission objectives. So now you're going to observe algal blooms. Now you're going to observe floods. Now you're going to observe ice jams, and so on and so forth. Okay, so this is kind of like the summary of the main elements in this 3D chess project. The two enabling technologies that I'm going to talk about today are a new type of reasoning, or relatively new type of reasoning techniques that are based on knowledge graph reasoning that combine something called embeddings with logical rules, which is kind of like the good old-fashioned AI. And then decentralized coordination strategies. And in particular, we're going to look at consensus-based task allocation algorithms and compare that against other kinds of decentralized coordination strategies. In order to achieve that proof of concept, we're going to rely on a multi-agent simulation. So we build a simulator where different agents or different 3D chess nodes can be, different types of platforms, spacecraft, UAVs, ground sensors, and they're all modeled in terms of this internal structure that has 3 different modules. The engineering module is basically the simulator of the platform and the sensors. So if you were actually flying this software in an actual satellite or actual UAVs, you wouldn't need the engineering module. That's what you need to simulate all those platforms. And then we have the science module, which is what does the onboard data processing, essentially, and the planning module, which is essentially what decides who's going to do what and when. So the science module and the planning module would be the flight software if you were to actually fly this. So these were our objectives. We were trying to look at the feasibility and the value of implementing this kind of technology in the context of the inland water ecosystem. And in particular, we wanted also to study, we recognize that this is a pretty bold concept, pretty different from the way things are done today, where there's none of these planning and scheduling. Pretty much for the most part, satellites are being, they have a very static ConOps where they just look down and gather data. And then when they're on, invisibility of the ground station, they dump all the data they have. And, if for whatever reason, operators want to change that ConOps and say, do a slewing maneuver on a spacecraft to point at a different location to observe an event, they're going to manually upload those plans, right? So here we're trying to, significantly change that. So we wanted to look into basically intermediate concepts where we look at transition architectures that are somewhere between 3D chess and the status quo, and then also looking at federated architectures where perhaps different assets from different organizations, say ESA and NASA spacecraft, can temporarily enter these 3D chess coalitions to collaborate on, observing a specific event. So just to clarify a little bit what this concept of operations looks like. So this is kind of like the main steps. So initially, each platform in the network is performing their own nominal mission. So in this case, we could be, providing global observations of inland water quantity and quality. So quality would be essentially looking at the color of the water with different types of spectrometers for things like, sediment concentrations, chlorophyll concentrations, and things like that. And then, like I said, there's nodes of different types. So some nodes actually perform onboard data processing. Probably all nodes have some kind of observation capability and communication capability. So let's imagine, just for the sake of argument, that one of the things that we're interested in is detecting algal blooms as one of these events of interest. So this could be, as an example, an algorithm that could be applied. So from the main raw data that is being measured by the visible near infrared sensor, what you get is actually radiances. It's the amount of radiation, essentially, in a specific spectral band. So there's algorithms, simple algorithms that essentially perform differences in ratios of radiances in different channels to obtain estimates of chlorophyll A concentration. And then based on the time series of chlorophyll A compared to historical data, you can decide if there's something that's, an anomalous sudden change in chlorophyll A, which is indicative of the onset of an algal bloom. So when that happens, then the sensor that detects that event of interest is going to share that information with the rest of the network. We're going to see different ways that we can do that, either immediately as a task request for the other sensors to essentially re-observe that same location with perhaps complementary sensors to improve spatiotemporal sampling, or just sharing that information periodically so that sensors in the network can individually replan, and we'll see how those two kind of compare to one another. But here's an example of what that event observation information may look like. There's the potential algal bloom event at a certain latitude, longitude with a certain severity, perhaps calculated as a fraction of lake area affected, and also including the actual intensity, the growth rate, and perhaps if the lake is used for actual drinking water or what it's actually used for. And that could generate a task request. Again, all of these needs to be completely autonomous, right? Which is where the challenge is. To measure water level and temperature, which could be two data products, two geophysical parameters that are related to these algal blooms and have not been observed yet with this particular sensor, with a certain spatial resolution, say better than 100 meters within the next 6 hours. So that's kind of what would be shared. And then the nodes would receive this task request, and they would use this context information, which is essentially a knowledge graph or a knowledge base if we add other things that are not explicitly included in the knowledge graph, and would use reasoning algorithms to autonomously determine if they can perform the task. So this is what replaces the human operator making the calls of, which satellite they're going to replan to observe this particular event. So this kind of requires this knowledge graph that contains information about the capabilities of the not only that particular agent but other agents in the network. And then importantly, it also contains information about how data products can be obtained from other data products. So in Earth observation, there's a concept of different data product levels. Level 1 would be radiances. Level 2 could be, say, water levels. Or water temperatures. Level 3 could be something higher level than that. So the idea is that using this knowledge graph, the agent should be able to autonomously determine that they can perform this particular task of measuring water temperature, even if they didn't necessarily initially know. They only knew that they have a tier sensor, and they had no fact explicitly mentioning in the knowledge base that they could measure water temperature. They can infer that they can measure water temperature from the fact that water temperature is related to thermal infrared radiances. So that's kind of the idea. So with that purpose, we built a knowledge graph, primarily mining information from a database, an online publicly available database put forth by the Committee on Earth Observing Satellites. That contains information about the current and planned satellite missions, their sensors, and the data products. So that already gave us a lot of information, but we were still lacking some information about how data products relate to other products. So what we did is try to mine directly from papers, actually from all of the abstracts in the IEEE. Actually, then it became really all the papers, not just the abstracts, in the journal called IEEE Transactions on Geoscience and Remote Sensing. So we did this several years ago. So we were not using the the state-of-the-art tools based on GPT-4 and so forth. So we're trying to redo that now to, instead of using SPACY, which is older NLP kind of stuff, natural language processing libraries, we're going to use GPT-4 and retrieval augmented generation strategies to improve that. But the idea is that we can automatically extract triplets from these papers and assign a certain confidence score based on the uncertainty information provided by these libraries. So we can maybe infer that, Poseidon, which is an existing altimeter, can measure sea level with certainty 1 because that comes from the CEOS database, and that's a proven thing and the thing that's actually flying right now. But for other triplets, there may be some uncertainty. So whether this instrument called Severi can actually measure vegetation state, that's assessed at a level of 0.46. So this was implemented in a tool called Neo4j to develop graph databases to get a sense of the size of this knowledge graph. It has a few thousand nodes and relations. And then we can use different types of algorithms. So this is one algorithm that we've been using that's called UKG, developed by our collaborators at the University of California, Los Angeles. So this is a method to calculate embeddings. So embeddings are basically latent space representations as vectors in Euclidean space in Rn, essentially, of these triplet information. So a triplet is something like observes sensor tier radiance, which has a relation and then two entities, the head entity and the tail entity. So each of these entities and each of these relations has a vector in Rn associated with it. That's called the embedding of that entity or that relation. And those embeddings are actually learned to minimize some kind of loss function. So in this case, the loss function is depicted here. So it has a component where you're just trying to minimize the mean square error of the confidence scores as provided in the uncertain knowledge graph. And then there's a certain term in this loss function that corresponds to the triplets that were not observed in the knowledge graph. And for those, what we're trying to do is to minimize the distance to satisfying a set of logical rules provided. So there's a number of logical rules, like, if you're an instance of a sensor type and the sensor type is known to be able to measure something, some observable property, then this instance of the sensor will also be able to observe that property. So that's an example of the rule. So by minimizing these two terms, essentially you can come up with embeddings for these triplets in the knowledge graph, for these entities and relations that allow you to essentially do what we call knowledge graph completion. So essentially infer what is the probability of a certain missing triplet in the knowledge graph to actually be true. And so that's what we did. We got a mean square error over a test set of 10% of the triples of about 0.04. So you take the square root of that, that's 0.2. So it's not great. That means that, if something has an actual confidence score of 0.6, you could think that it's 0.8 or 0.4. But for the purposes of this application, is sufficient, because you're just trying to decide if a particular sensor can actually perform or help with a particular task. So false positives are not a big concern in this application. The next step is the decentralized coordination piece. So here is where all of the sensors that have determined through the process that I just described that they can perform or help with a particular task, they are actually going to enter a next phase of decentralized coordination. So this is when they're going to actually decide who's going to do what and when. So we're looking at two different approaches for this that you're going to see in a second. One is just periodically sharing information about the event observations and then individually replan. And then the other one is using what is known as consensus-based task allocation algorithms, which is very well known in UAVs and robotics as a task allocation algorithm for heterogeneous systems. So we'll see how those compare. But the idea is to use science-driven utility function to inform those planning processes. So take into account not just the priority of those tasks so that you can weigh them against any current tasks that you're doing, but also the expected performance of each of the agents in the task, depending on not just the type of sensor that it has, but also the relative geometry, say, incidence angle, range, and so forth. And then, of course, the cost. So we want to be efficient. So if there's two equally good alternatives to do a solution, to do a measurement, and one of them requires less energy, that would be preferred. So we're going to see what those look like in a few slides. This is kind of like the science-driven utility function. I'm not going to go into the details in the interest of time, but if you're interested, I'm happy to answer questions. The idea is basically to look at different science objectives and look at the different requirements for each of those science objectives and see if they're satisfied or not, kind of thing. Okay, so with that concepts out of the way, we can go into explaining a little bit what the simulation tool that we built looks like. So like we said, this is a multi-agent simulation that's building upon Python's native asynchronous functionality. So there's different agents that coordinate by exchanging messages. So you can actually use two mechanisms to exchange messages. We have a peer-to-peer kind of mechanism where you can communicate with a single other agent in the network. Or you can broadcast a message to the entire network using different types of ports, as you can see here. So the agents in the simulation, of course, are the different nodes in the network, but there's also a few special kinds of agents like the simulation manager, logger of the results, and most importantly, the environment server, which is essentially simulating the environment and providing the simulated measurements about water level, water quality, whatever it is, to the different agents via these messages. All right, so that's basically the general background for this, and I'm now going to go into a succinct description of the preliminary results. So this is all work in progress, but we're getting pretty exciting results, and I'm happy to share those with you today. So I'm going to start with that periodic information sharing and replanning kind of strategy. So the idea here, we call it basically the shared reward grid. So every few minutes, each satellite in a constellation is going to broadcast any information about events observed during the last time period. And as a result of that, every agent is going to update the reward grid to increase the reward for observing a particular event. If there's a point on the grid that was not an event and now becomes an event, the reward is going to go up for that particular point. And then, there's other kinds of adjustments that are going to happen to that reward grid. If a point that was not observed is observed and there's no event, the reward is going to go to 0. For all the events, the reward is going to go down following a linear trend. And so on and so forth. And then based on this reward grid, the idea is that the agents are going to individually replan. So instead of solving the centralized task allocation problem, which is not tractable really due to the size of the network in general and the number of contact opportunities that we have, each satellite is just going to look at their own side of the problem, but using information from everyone else, if that makes sense. So the algorithm that each satellite or each agent more generally uses to do the planning is based on dynamic programming, which is a very well-known algorithm for solving Markov decision processes. So the idea is that you construct a graph. Each node in the graph is a potential contact opportunity to observe a particular point with a particular reward. And then the edges here represent valid transitions, taking into account all of the constraints, and in particular, the slewing constraint. So the fact that there's no direct node from A to B in this graph here means that I can't slew fast enough to go from A to B. As you can see in this map, if I choose to observe A, I would have to slew really, really fast to also observe B. So that's not going to happen. So there's no edge from A to B, basically. And then the idea of this approach is just to use dynamic programming to optimally traverse that graph to maximize the reward kind of thing. So this is the overall replanning strategy. So the reward grid is initialized so that every point has an initial reward of 1. And then the dynamic programming planner is invoked in each of the agents. The plan is executed. And then every certain sharing period, whatever that is, 10 minutes or whatever that is, satellites share information about the points that they have observed and where they have seen events and not seen events. And as a result, the reward grid is updated on each of the agents, and then they go and replan again. So you can kind of see here a little bit of what's happening. This is particularly looking at the satellites. This is the field of regard of the satellites, so they can see anything within that field of regard. But if they choose to observe one thing within their field of regard, they may not be able to observe something else on the field of regard because of the slewing constraints. So here there's two important parameters. One is, my student called it planning horizon, but I think it's best described as the period with which you invoke the replanner, which in this case is equal to the planning horizon, but doesn't have to be. Obviously, this does not necessarily improve performance. So if you imagine what's happening here, the underlying reward structure is not static, right? So rewards change over time as agents gain new information about events of interest. So if you take a longer planning horizon, that means that you also take longer to replan. So that may not play in your favor. What pretty much always helps is decreasing the sharing period or increasing the sharing frequency. So, if you share information every 100 seconds instead of 1,000 seconds, for example, you go from 475 unique events to 642, or for the total number of event observations, you go from 1,100 to roughly 2,500. This is for a particular scenario where we're interested in fire with 24 satellites and 8 planes and a specific agility of 1 degree per second, field of regard of 60 degrees and field of view of 5 degrees. We did a bunch of simulations under a wide range of conditions. You're going to see that in just a second. So this is actually a parametric study that we did. So rather than looking at specific events that have specific properties like duration, quantity, and so forth, we kind of like abstracted out what are the main properties that define events in terms of duration, frequency of events essentially, or quantity of events per day, whether they're uniform or clustered. And then we also looked at key parameters in the observing system. What is the agility of the satellites in particular? What is the field of regard? What is the field of view? How many planes? How many satellites per plane? And then how many observation types are needed? Do you need 2 types of sensors, say visible and near and thermal infrared, or 3 types if you also need water levels with a radar altimeter, and so forth, or 4 types. So by and large, the result of implementing this reactive planning strategy versus a non-reactive planning strategy, where you just plan ahead of time to observe all of the rivers and lakes, is always positive, but the magnitude of the improvement really changes depending on the specific values of these parameters. And actually, it improves more for longer events and larger constellations. The idea being that if you have longer events, you have a little bit more time to react to them. If you have larger constellations, you have more assets that can respond to them, as you would expect. This is a particular example for one case looking at precipitation events. And we can see here that for this particular case, there's a very significant improvement in terms of the number of events observed. So it goes from 1607. Sorry, it goes from 52 if you only do initial planning to 1607 if you do replanning, which is a huge improvement. This is with the same constellation, so ISO constellation. And if you want to know how it compares to what we do today, which, for example, you could say using Landsat, this would be only 5 out of the 5,000 being observed. We did the same thing looking at different requirements for the observation. So if we require different types of sensors, not just one, to consider an event fully observed, then it's even more difficult to perform these co-observations. And actually with pre-planning, there's 0 out of the 355 possible rain events co-observed. If you do the reactive planning, you get 13 out of those, which is not great, but 13, much better than 0, right? Okay, so that was all based on that, periodic information sharing and replanning. We also wanted to look at this idea of consensus-based task allocation, which is very popular in the robotics and the UAV kind of literature. So for that, we implemented an asynchronous consensus-based bundle algorithm. So there's different variations of this consensus-based bundle algorithm. The original algorithm was developed by John Howe at MIT, looking particularly at UAVs. It has different, limitations in terms of the formulation that prevented us from using the original algorithm. So we had to use essentially a modified and asynchronous version of the CBVA. But basically the way it works is that agents iterate back and forth between 2 phases, phases where they're building a bundle of tasks. So the agents are actually considering multiple tasks at a time, and the size of that bundle is going to be an important parameter. And then once they have a bundle of tasks that is built, they provide a bid for that particular bundle. So that means essentially based on the performance with which they can measure those tasks. They come up with a number, send that to the other agents in the network, and then we get into this consensus phase where nodes exchange information about their bits. So know that that's very little information, right? So one bit is one scalar number compared to, sharing other things that they could share about their capabilities or, the things. So this is very little information that is being exchanged. And then there's iteration, basically within the agents in the network to determine, who basically has the highest bid, so who gets to do what kind of thing. So this is pretty much where we are right now in terms of this thing. We're replicating the parametric study that we did with the periodic information sharing and replanning, but doing it with the CBBA type. Initial results of the algorithm are also promising, but they're actually very interesting from the perspective that they show more clearly a trade-off between exploration and exploitation. So if you think about it, the CBBA, it happens in real time. It doesn't wait for those synchronous times to share the information and replan. So any time where there's a task request, someone in the network is going to be moved away from whatever it is they're doing to respond to that event of interest. And that has, as a result, a positive impact on basically this metric of what are the fraction of events co-observed, compared to the ones that are actually co-observable and detectable. However, that has a negative impact on the potential discovery of new events, right? So you could characterize that as hindering exploration, to benefit exploitation of these known events of interest, right? So this is something that, to some extent, with the current mechanism is unavoidable. You can have some weights in terms of how you define those rewards to weigh exploration against exploitation, but there's not much more that you can do for that. We'll talk, in the next steps slide about something that basically tries to make the most of the two worlds, basically having a hybrid agent that uses the two strategies, the dynamic replanning with periodic information sharing, and also the CBBA in between. The other thing that we've done, and this really started primarily as a benchmark idea. So our idea was to try to see how these methods, which are all decentralized, would compare to an optimal centralized task allocation strategy, right? So we're looking essentially at integer programming techniques, which are guaranteed to give you the true global optimal. And that way we can compare the optimality of decentralized strategies against the actual optimum. So that's really how it started. We also then looked at the feasibility of doing this on board, and I'm going to show you what that looks like in just a second. But this is kind of the formulations. There's different types of formulations, but they all look very similar. So we're trying to maximize the total reward here, which you can see the RTIPX. T is time, I is the location, the ground point in the grid, P is a pointing option, S is the satellite index, and X is the satellite type or sensor type index. A here is a parameter matrix that basically contains the information about the contact opportunities, which satellites could see which points at which times with which pointing options. OTPS are the control variables, the design variables, basically. So is satellite S using pointing option P at time T kind of thing. And then YSX is just the mapping of the sensors to sensor types to satellites. So essentially, this is maximizing reward subject to constraints. You can only point in one location. Each satellite can only point in one location. You can only look at things where you have contact opportunities for them, and then the slewing constraint. So there's an additional constraint that we experimented with, which is this one right here, which is constraining the maximum number of observations of one type that you get of each particular ground point. It turns out that adding this constraint induces something similar to a unimodularity kind of property in the program that makes it solve much, much faster. You don't strictly need this in terms of modeling. This is not something that we necessarily wanted, but adding these constraints does significantly increase the speed. Similarly, if instead of a maximum torque constraint, if you use a maximum slew rate constraint, which is linear, that has a positive impact on the runtime. By and large, results are as expected. Of course, the integer program has a better performance compared to other approaches, say greedy forward search, that you could do from a decentralized and centralized perspectives. However, the problem is that depending on the number of ground points and contact opportunities that you get, sometimes you just can't really solve those integer programs, even for relatively short planning horizons of 1 to 2 hours. All right, so I think this is my next slide. So in terms of next steps, I think I've mentioned them kind of along the way, but we're looking at improving the automatic extraction of the triplets for the knowledge graph from papers using LLMs and RAG, and in particular using GPT-4 and LangChain for that. And that's looking pretty promising. We kind of went down a rabbit hole there, trying to develop different ways of computing embeddings in the presence of numerical attributes, which is somehow became the master thesis of one of my students. Even though we're not necessarily working in that area, it turned out to be a pretty promising idea. We are, as you can see from the results, we're not quite done in terms of benchmarking these different decentralized strategies and centralized strategies against one another, but it's just a matter of finalizing these results. Something that I haven't mentioned explicitly is that all of the results that we have obtained so far assume perfect communications, right? So agents in the network can communicate anytime they want, and there's no latency and no bandwidth limit. Right, so that's obviously not realistic. And as you incorporate, realistic constraints in terms of line of sight, if you're not using a relay service, non-zero latencies, limits in bandwidth, all of that could affect the coordination strategy by introducing an information asymmetry and lead to suboptimal performance in the task allocation. Another thing that we're trying to do right now is actually using reinforcement learning strategies to solve this problem. So I actually have a couple of students looking at different ways that you can do this. In particular, one of them is using transformers, which are a specific type of neural network that is typically based in language tasks, but using it for, essentially solving this MDP. So essentially, transformers are really good at sequence modeling kinds of tasks. So we're looking at the problem as a sequence modeling kind of problem. This is a project that's going to end, in the summer, but the continuation has already been awarded, and we're planning on incorporating predictive models and data simulation. So one big important limitation that we have right now is that we cannot really predict events of interest before they are detected, before they occur. So if really what you're after is improving response time, being able to predict events of interest before they occur could actually have a much larger impact on response time than just coordinating after they have occurred, where the options that you have to coordinate may be limited depending on the size of the constellation and so forth. We're also looking at decentralized estimation and calibration. So this is also something that we have ignored so far. If one agent, basically tells everyone, determines that there's an event of interest somewhere, that's based on their own unique observations, but we have potentially observations from other agents that could contribute to deciding whether or not that is an event of interest. So that's what we call this decentralized estimation and calibration. And we have a group at UCLA working on a decentralized Kalman filter approach for this. And then the next thing that we want to do in this new award is actually doing hardware in the loop testing. So we're going to implement the flight software on small quadcopters. I actually recently purchased a motion capture system in my lab to do this. And we'll have a terrain simulator also that some of my undergrad students are building right now. And we're trying to basically just demonstrate the CONOP. So demonstrate the ability for these quadcopters to detect some event of interest. So in particular, we're looking at generating fake floods in our terrain simulator, and then having them coordinate to provide complementary observations. So with that, this is a few publications that have come out of this project, a few acronyms, and I'll stop here and see if there are any questions.